Hi Wildcats, this is Unit 2, Focus Question 5, and in this video I want to go over electromagnetic waves and how they are similar and different to mechanical waves. So, electromagnetic waves are sometimes more commonly referred to as electromagnetic radiation, but those two terms are synonymous. So, first, let's start with what is electromagnetic radiation or electromagnetic waves. So, just like the mechanical waves we have been looking at, electromagnetic waves are caused by vibrations. So, in mechanical waves, it's some physical medium or particle that vibrates. So, say an air molecule or a water molecule vibrating, and the energy moves through that. Electromagnetic radiation is similar in that it is a vibration, but it's different in that this time it is the actual um, vibration of atoms or the particles that make up an atom. So in this picture here, you can see that we have a regular atom and it has the nucleus and electrons around it. And you might recall from chemistry that when an electron gains energy, it can bounce up to a higher orbital. And in doing so, right, this is kind of, it goes up and then drops back down. So as it absorbs energy, it goes from this inner orbital to this outer orbital. So now it's vibrating up, and then that energy is given off and it returns back to its ground state. So here's the emission of that energy. So in the same way that a water molecule vibrates back and forth, up and down, or the atoms in the spring that we've used have vibrated up and down, you get that same thing. It's just now with an electron. So it's similar in that it's caused by vibrations. It's different in that it's not a whole molecule. It's just the electron in vibrating back and forth between the orbitals as they gain and lose energy. That causes an electromagnetic wave. Electromagnetic waves are different in that they have both an electric and magnetic field. So it's kind of hard to visualize it first, and pictures sometimes don't exactly do it justice. So, but these are the best that I can find. So in here, you've got to think of this as this is going up and down. So this is Y, and this is the Z axis. So coming in and out of the page. And what you have is two fields at the same time. One is this oscillating electric field up and down, and one is this oscillating magnetic field in and out of the page. And so you get what looks like this. So you can see at the same time, we have two um, we have the field in both the Z and in this case the X, and you can see it's going up and down and in and out, vibrating back and forth, and that results in our electromagnetic wave. So I know that's a little funky to think about at first, but it is just two fields, electric and magnetic fields, and they are perpendicular to each other. So in this case, up and down and in and out of the page. Okay, so what else is different about electromagnetic radiation? Well, one thing, the biggest thing is electromagnetic radiation does not require a medium to travel through. So up until now, our mechanical waves have required a medium. They do require a medium, whether that be sound through the air or a wave through the water, whatever. Mechanical waves have to go through something. Electromagnetic radiation does not. Okay, so that's why like light, which is an electromagnetic wave, can travel through the vacuum of space because there's nearly nothing in space for it to travel through, and yet clearly light, electromagnetic waves in the form of light from the sun can get to Earth. Okay, so that is the big difference between them. A similarity is that they still have frequencies and wavelengths. So here you can see two different waves. This one has a different wavelength than this one. It has a different frequency as well. Another difference is that all electromagnetic waves in a vacuum have the same speed, and that speed is 3.00 times 10 to the 8th meters per second. It is literally the fastest thing in the universe. It is the speed limit of the universe. Nothing that we understand can go faster than that speed, 3.0 times 10 to the 8th meters per second, or the speed of an electromagnetic wave. You might have heard this referred to as the speed of light, but that's just because light is the form of electromagnetic radiation that we're most familiar with, so it gets called that, but this speed applies to all electromagnetic radiation or electromagnetic waves. Okay, so here are all of the um, electromagnetic waves across this spectrum. Um, to note, these are arbitrary divisions that we humans have created to make our lives easier as we understand these, but this is really a spectrum, so it goes all the way across here. Visible light is the one that we can see with our eyes, so our eyes are actually sensitive to this, but there are lots of them. So UV rays we are familiar with, they give us sunburn. Those are just to the left in this image of electromagnetic or of visible light. There's X-rays, gamma rays, and then if you go this way, you have infrared, microwave, radio, and long radio waves. Okay, so as we look at this chart, we can see that there is frequency listed as well as wavelength. And so when you look at these, what do you notice about the frequencies as they go across this, as we move from left to right? And one thing you can observe is that it is getting smaller. So the frequency of a gamma ray is really, 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 really high. So 10 to the negative 10 to the 24th. And as we move this way, it gets smaller and smaller. So 10 to the second hertz. Wavelength is the opposite. So when frequency is really high, wavelength is really small. So in this case, when we have gamma rays, say 10 to the 24th. Their wavelength is teeny, teeny, tiny, 10 to the negative 16th. And as the frequency goes down, wavelength goes up. So that should tell us that there's a relationship between these two